So welcome to my channel on technology space with machine learning and artificial intelligence. So the today's topic is what is the fuel life cycle in shipping? And today we are starting a new playlist on decarbonization. In this discussion, I would expect to introduce some of the theories related to the thermodynamics that can be utilized towards the decarbonization of the shipping. Because of that same reason, I would keep this playlist as a separate one from the maritime technology playlist. So hopefully you will enjoy these videos also. Let's move on to the main content of this presentation. So let's try to answer the main question of why this is an important concept in the shipping industry. When you're looking into selecting energy efficient and emission reduction technologies for new built and existing vessels, there must be some type of a decision making process. So this decision making process somewhat based on the cost and emissions associated with the respective technology, and not just the technology itself. These technologies might associated with different fuel types also. Therefore, the cost and emissions associated with these respective fuel types will play a crucial role in the decision making process of these technologies eventually. Therefore, we can classify that the life cycle of each fuel can play an important role in this process of decarbonization. So let's try to answer the main question in this presentation. What is the fuel life cycle? So the fuel life cycle is this life path of the respective fuel from its birth at the oil and gas fields to its death. At this point, this process consists of transforming this chemical energy in the fuel into a mechanical energy in the vessel as ship speed. So this process consists of many steps. Let's go through these steps. When you're looking into the life cycle of a respective fuel, we often interested in quantifying that life cycle with respect to some type of a monetary value. That means the cost associated with this life cycle can tell us how cost effective such type of fuel that can be utilized with the relevant technologies. So there are important factors we should consider when we are doing such type of a calculation. So the first factor would be how much emission being released into the environment. So the second would be how much mechanical and electrical energy being released into the environment due to various losses. And then third, this operation and maintenance cost. Here we are referring to these fuel storage and handling facilities and then their associated cost as the operation and maintenance cost for this fuel life cycle. So eventually these emissions and then mechanical and electrical energy losses can also be quantified into some type of environmental cost as well as energy efficiency cost. Then you can add up all these costs towards the final calculation. So let's try to go through the fuel life cycle. Here I am presenting an oil and gas field extracting crude oil and gas. So this is the birthplace of such type of a fuel, and this can be either onshore or offshore. So this platform release emissions. These emissions can be classified into many groups. Here I am representing CO2 and nitrous oxide, which is the industrial word would be NOx, and there can be a sulfur oxide also, even though I'm not representing here. This sulfur oxide can be classified as a SOx, and then methane can also be released into the environment as CH4. So this platform often associated with the operational and maintenance cost. So that should also be considered when you are looking into the fuel life cycle. As the next step, this crude oil and gas should be delivered into an oil refinery from the oil and gas field. That can be done by ocean-based or land-based transportation system. Here I am presenting this oil and gas tanker is delivering this crude oil and gas into the oil refinery. So during that process, these vessels or vehicles will deliver emissions into the environment, and there are operational and maintenance costs associated with these ocean or land-based transportation systems. So as the next step, this crude oil and gas being delivered into the oil refinery, being separated into light, middle and heavy distillates. So this is where these different types of or different grades of fuel being created by the oil refinery. And then that during that oil refinery process, some of the carbon content and sulfur can be separated from the respective fuel. So this way you can create somewhat cleaner fuel through this oil refinery process. During this process, there would be emissions being released into the environment by this oil refinery, and then it also associated with operation and maintenance cost. So as the next step, these distillates should be delivered from oil refinery to the bunker fuel pump and eventually into the tank in these vessels. So this delivery process can happen in land-based transportation system as well as ocean-based transportation systems. So here I am representing a fuel delivery truck as the main transportation system for this distillate delivery. So during this process, these vessels will deliver emissions into the environment. And then this delivery process will also be associated with operation and maintenance cost. So far I have described that extracting oil and gas from the respective field and to deliver into the bunker fuel pump and tank. So this process is called this well to tank process. Often when you want to do calculations for the emissions as well as the operation and maintenance cost, we separate this well to tank process as a upstream part of this fuel life cycle. So let's try to look into the downstream part of the fuel life cycle. This is where these marine power plants will play an important role. These power plants can consist of main and auxiliary engines, multiple types of engines with respect to the power requirement of these ocean-going vessels. And these engines will transfer this chemical energy in the bunker fuel into a mechanical energy that would drive these vessels forward. And then this chemical energy transformation into a mechanical energy being done by the combustion process of these marine engines. During this combustion process, of course, there would be emissions being released into the environment. And then at some point, some of these emissions can be cleaned by different emission cleaning technologies. And cleaned emissions can be released into the environment as exhaust gas. And then some of these exhaust gas can be recirculated within these marine engines. So that way, the amount of emissions you are releasing into the environment can be reduced. During this combustion process where this chemical energy has been transferred into a mechanical energy, there are some amount of energy being released into the environment as this mechanical and electrical energy losses. And then there are some energy recovery technologies being developed to recover some portion of this energy, and that can be fed back into the marine power plant as recovered energy. Of course, some amount of energy will still be released into the environment as energy losses. And then there are operation and maintenance costs that are associated with these marine power plants also. So let's look into the next part of the fuel life cycle. In this situation, the mechanical energy that has been created by the marine power plants being transferred into a propulsion thrust by a propeller. In this situation, I am assuming that this vessel is facilitated with the propeller, and then of course the propulsion configurations for these vessels can vary. And then that propulsion thrust being transferred into ship speed. One of the biggest challenge in these propellers would be fouling and cavitation. So if that has happened, there will be mechanical energy losses being occurred during this process. This propulsion thrust eventually pushed these vessels forward to create this ship speed. So since these vessels are moving in a water surface, the water surface will work against these vessel motions as ship resistance. This ship resistance somewhat related to the water depth of that environment as well as the trim and draft conditions of these vessels. And then there will be encounter ocean wind, wave and current conditions, and these conditions would introduce additional ship resistance or added ship resistance into these vessels. Therefore, when you adapt these ship resistance and this added ship resistance, that can also be considered as some sort of a mechanical energy losses during this fuel life cycle. In addition, there would be operation and maintenance cost also associated with that, and I am referring to these costs as the fuel handling and storage cost for these vessels. So in the second part of this presentation, we have discussed this bunker fuel in the tank being transferred into a ship speed. That has happened through the chemical energy in this bunker fuel being transferred into a mechanical energy of these vessels through these marine power plants. During that process, we have discussed that the emission being released into the environment, and then there are mechanical and electrical energy losses also happening. In addition to that, there are operation and maintenance costs being associated with this process also. So this part of the process being called as a tank to propeller process, and this is also the downstream part of the fuel life cycle. So if you combine the upstream and downstream part of the fuel life cycle, you will end up with the complete life cycle itself for the respective fuel. So that's the end of my presentation. Hopefully you have enjoyed this presentation also. So if you are interested, please stick around. Thank you.